everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So we're going to look at the nature of the bonding in a benzene ring, limited to the planar structure and bond length intermediate between single and double, and then the delocalization of p electrons, which makes the benzene more stable than the theoretical molecule cyclohexa-135 triene. So by the end, we should be able to use thermochemical evidence from enthalpies of hydrogenation to account for this extra stability and explain why substitution reactions occur in preference to addition reactions. So now I'm going to introduce aromatic chemistry. So arenes are compounds which contain a benzene ring, which is C6H6. And so aromatic compounds are compounds with this benzene ring. Phenols are a type of these compounds, and they're actually a benzene ring with an OH group attached. So here we have the skeletal formulas of benzene and phenol. So benzene is C6H6. So what it actually looks like is we have 6 carbons. So 1, 2, 3, 4, 5, 6. And then they're all attached to one hydrogen each. And they're all single bonds. So this will be the displayed formula of benzene. And then the skeletal formula for phenol would be the same, but with an OH instead of one of these hydrogens, because one of the OHs replaces a hydrogen. And we're going to talk later about why we have a circle in the middle of the hexagon. So now we're going to look at the structure of benzene. And what you need to know is that one electron from each carbon atom is delocalized above and below the benzene ring. And so there's overlapping of p orbitals to achieve this. And so as you can see, for one carbon here, for example, for this one, it's got 3 bonds. So it's got 2 of these carbon-carbon single bonds, and it's got 1 carbon-hydrogen bond. And we all know that carbon is in group 4. And that means that it can form 4 bonds. And because it only forms 3, that means that we get 1 electron, which is going to be delocalized. And so here, all of these red shapes are the p orbitals. And what the green lines indicate is the overlapping of these orbitals. And so in equations, we write benzene like this. So we use the structural formula. And the circle actually denotes the delocalized electrons. So things you need to know about benzene are that it's a flat hexagonal ring of carbons. And each carbon atom is singly bonded to a hydrogen atom. The delocalization of electrons occurs above and also below the ring, and so this adds stability to the structure. Each carbon has 3 covalent bonds, so it has 1 to a hydrogen and 1 to 2 other carbon atoms, and this means that the 4th electron is involved with the delocalization. A really important thing, well, 2 really important things to know are that the carbon single bond lengths in benzene are in between the lengths for a carbon-carbon single bond and a carbon-carbon double bond. And also each bond enthalpy, so each of these carbon-carbon single bond enthalpies in benzene is between a normal carbon-carbon single bond and a carbon-carbon double bond. And now looking at the physical properties of arenes. They are colorless liquids at room temperature. And they boil at 353 Kelvin and freeze at 279 Kelvin. So they've got quite high boiling and melting points. And benzene's flat hexagonal molecules pack together well in the solid state, and therefore more energy is needed to break the van der Waals forces between the molecules. So this explains why it's got such a high melting and boiling point. And another thing to know is that arenes will not mix with water. However, they will mix with other hydrocarbons and other non-polar solvents. And this is because we can't form hydrogen bonds with the water, and so it can't mix with the water. And the key point is that substitution reactions tend to happen instead of addition reactions, as addition reactions would involve an input of energy to overcome the delocalized electrons and break the ring. And this energy needed is called the delocalization energy. And so if you think back to reactions with alkenes or something with a carbon-carbon double bond, we normally get an addition reaction because we add across the double bond. However, for benzene, we tend to get substitution reactions because it takes quite a lot of energy to overcome the delocalized electrons to break the ring. Now we're going to talk about naming aromatic compounds. So it's a bit more complicated compared to naming alkanes or alkenes or anything that we've seen before, because sometimes it can vary. But for some general rules, the first is that aromatic compounds are often named as derivatives of benzene. And so benzene forms the root of the name. And what we mean by this is just that some of these aromatic compounds we kind of get from benzene. So that's why I put benzene in the root of the name. So for example, we could have a benzene ring, and we could then have a chlorine attached, and we would call this chlorobenzene. So because it's derived from benzene, we put benzene in the root of the name, so the main part of the name, and we have chloro as some kind of substituent. We can also get benzene with a methyl group, and we call this methylbenzene. So like when we name branched alkanes or branched alkenes, we label the substituents. So this would be methyl. And one thing to note about these is that we don't need a number because there's only one substituent. And this is actually also called toluene. We can also get benzene, but with a carboxylic acid group attached. And this is benzene carboxylic acid. And the final example I'm going to look at is nitrobenzene. So we have a benzene ring, and then we have an NO2 group attached. So this is nitrobenzene. And this is what we form when we go through nitration with benzene. And then the second rule is that if two or more substituents are present on the benzene ring, their positions are indicated by numbers, so very similar to when we label substituents on alkanes or alkenes, and we give the lowest possible numbers to the substituents. And so we're going to have a look at some more examples. So we could have benzene, and this time we'll have a CH3 and another CH3 here. So what we would do would be to first number them, and we can kind of see that the smallest possible numbers for these two substituent groups would be 1 and 3, because we would have carbon number 1 here, and then 2, and then 3, because any other numbers that you give them will be higher than 1 and 3. And so what we have here is 1,3-dimethylbenzene. So it's very similar to when we were labeling substituents for alkanes and alkenes. When we have different substituent groups, so you can have a benzene, and say we have a chlorine here and a methyl. Now we have to name them in alphabetical order. So this is our next rule. And so what we get is first we need to label the carbons so that these two substituents have the lowest numbers. And so we would naturally label one of them 1, and then we would go around 2, 3, 4. And you can see that if we went the other way around, so if we labeled them anti-clockwise, we would still have the other substituent on 4, and so it must be 1,4. And so this would be 1-chloro 4-methyl benzene. But in some textbooks, they might call this 4-chloromethyl benzene because they just assume that one will be either the chloro or the methyl. And so you only need the number for the other substituent group. So the next rule is that the benzene ring can be regarded as a substituent on another molecule. So it's a very similar idea to when we have alkyls. And so, for example, C6H5 is known as a phenyl group. And so, again, looking at some examples, we could have the main chain being an amine. So we have NH2, and this leads to the benzene. And so we would call this phenylamine. Because this bit here is the C6H5 group. And we call this phenyl when it's connected to something else that takes priority. We could also have phenyl ethene. So you'd have CH double bond CH2, and then this carbon would be attached to a carbon of benzene. So this is phenyl ethene because we've got eth because we have 2 carbons here, and then phenyl because of this group here. So we're taking the benzene as a substituent of something else. So alkenes and amines both take priority over this benzene group. We also get ketones that do this as well. So we have, for example, phenylethanone. So we have a carbon with double bond O, and then we have a methyl group, and then this carbon will be attached to our benzene. And so this would be phenylethanone. And this is because eth is indicating that we have 2 carbons here. The phenyl is basically the substituent group on the carbon. And then we have the suffix of -one because it's a ketone. As well as all these examples, there is a really important example that we need to look at, which is benzene attached to an OH. And this is what we call a phenol. And sometimes this can come up in exam questions. So this is just one that you need to remember. As a harder example, we could have a molecule that looks like this. So we have the benzene, and this is attached to a carbon, which is attached to a methyl, and it's double bonded to a carbon, which is attached to a methyl and a hydrogen. So how we would name this would be, again, the alkene takes priority, and so that forms the root of the name. And so this benzene will be treated as a phenyl group. And so the name we give this is 2-phenyl butene. And we have 4 carbons in the main chain, and this is why we get bute, because we have 1, 2, 3, 4 carbons in the alkene chain. And then we have this double bond here on the second carbon, and this is how we get the 2. And then the phenyl is also on the second carbon, and so this is how we get the 2 here. Now we're going to have a look at the Kekulé structure of benzene. So initially, the structure of benzene is thought to be a ring with alternating carbon-carbon double bonds, which we call the Kekulé structure. So we can see it drawn here. And basically, if we were looking at the displayed formula, it would be still 6 carbons. But we'd have a single bond, and then a double bond, and then a single, and then a double, a single, and a double. And so what this would mean would be that we would have CH single bonds, very much like the structure of benzene that we know now. And the evidence for the delocalized model of the bonding in benzene, so the one we've seen, which is this one, where we have one electron from each carbon being delocalized and the p orbitals overlapping to form this area of delocalization in the middle. The evidence that we have for this model, instead of the Kekulé structure, is provided by data from enthalpy changes of hydrogenation and carbon-carbon bond lengths. So if we first have a look at the carbon-carbon single bond length in cyclohexane. So cyclohexane has the structure of 6 carbons. But unlike benzene, it has 2 hydrogens on each carbon. And so we've measured the carbon-carbon single bonds to be 0.15 nanometers. And a nanometer is equal to 1 times 10 to the minus 9 meters. So it's very, very small. And then the carbon-carbon double bond length in cyclohexene. So cyclohexene will be 6 carbons again. So I'm going to draw the structural, the skeletal formula this time. So we have 6 carbons, but this time we have 1 double bond. And this time we would have 10 hydrogens instead of 12, because the molecular formula for cyclohexane is the same as hexene. So C6H12. But the molecular formula of cyclohexene would be C6H10, because we've lost 2 hydrogens because we've got a carbon-carbon double bond. And this carbon-carbon double bond length is measured to be 0.13 nanometers. So it's a bit smaller than the carbon-carbon single bond. And this is because the bond's stronger between the 2 carbons, and so it kind of pulls the 2 carbons in. And so this is why the bond length is smaller. But when we look at the carbon-carbon single bond length in benzene, so we're now looking at the delocalized model of benzene. So this one here, we have that the carbon-carbon bond length is 0.14 nanometers. So we can see that this is between a carbon-carbon single bond length in cyclohexane and a carbon-carbon double bond length in cyclohexene. And so this kind of supports the idea that we've got this delocalized model. So before we talked about the first set of evidence that we have against the Kekulé structure, which is the carbon-carbon bond lengths in benzene. And so now we're going to look at the second piece of evidence that we have, which is the enthalpy changes of hydrogenation. So the enthalpy change for the hydrogenation of cyclohexene is minus 120 kilojoules per mole. So what the hydrogenation of cyclohexene is that we're just adding hydrogen to the double bond. And so we're forming cyclohexane from cyclohexene. And so if we were to take the Kekulé structure as the structure of benzene, we would expect the enthalpy change of hydrogenation for benzene to be 3 times this amount of the enthalpy change for cyclohexene, because we have 3 double bonds instead of 1. And so we'd expect it to be minus 360 kilojoules per mole. However, when we actually look at the enthalpy change for benzene, what we find is that it's actually only minus 208 kilojoules per mole. So it's a lot less negative compared to the Kekulé structure, so the theoretical structure that we thought it could have been. And so this tells us that the structure of benzene is a lot more stable due to the delocalization of electrons. And so this is why we take the structure of benzene to be this delocalized model instead of the Kekulé structure. So now we're going to look at the combustion of benzene. So arenes burn with a smoky flame, and this is due to incomplete combustion. And so we form soot, which is carbon solid, instead of carbon dioxide when we burn things completely with enough oxygen. And this occurs as we have a really high carbon to hydrogen ratio. Arenes can also burn completely, but this is very unlikely because we have this high proportion of carbon in the molecules. And so that means that we would need a very high proportion of oxygen to the hydrocarbon to get complete combustion. And the general rule we have is that the higher the carbon to hydrogen ratio, the sootier the flame. And so now we're going to look at an example of balancing an equation. So we've got the incomplete combustion of methyl benzene. So methyl benzene is just benzene with a methyl group. So we have a methyl here, and then we're going to add on some oxygen, and what we're going to form is carbon solid and also some water. And this oxygen will be a gas, and this will probably be a liquid. And then what we do is we just balance it. So for the benzene, we have got 1, 2, 3, 4, 5, 6, and 7 carbons. So we need 7 here. And now for balancing the hydrogens, we need to remember that on this carbon here, we don't have a hydrogen anymore. We have a methyl instead. And so that means that the total number of hydrogens is 5 plus 3, so that's 8. So we need 4 of these waters. And now we balance the oxygen. So we've got 4 oxygens on the right, and that means we need 2 oxygens on the left.